In this video, we are going to talk about an OLS regression that has been used when the dependent variable is a continuous variable and we have multiple independent variables. Okay. A technique for modeling linear relationship between the one or more independent variable and the one dependent variable wherein each dependent variable is evaluated on the basis of its ability to accurately predict, or sometimes we just explain, the value of the dependent variable. So the regression analysis, there are so many regression analysis. So the one we've been talking about in the PowerPoints here, when we talk about linear relationship, is the OLS regression or the linear regression. And in the logistic regression, we are going to talk about the binary logistic regression, which are like the very two basic regressions. Okay, so in order to explain what is a linear relationship, you can see here the relationship between the x, y is a linear. So you can literally draw a line and to see the relationship between the x, y, right? So if you remember what we talk about in the correlation, these pictures also look like the positive correlation in the correlation chapter. Okay, so if you have a linear relationship like this, also suggests a linear relationship, then that is like a negative correlation linear relationship, right? We also have some non-linear relationship. You can see all of these graphs showing the non-linear because you can't really use a line to represent the relationship between the x or y. I don't even know how to draw this one. Okay, these are not linear relationship. Okay, so when we had those points in the previous four hypothesis tests, whether it is the chi-square t-test, ANOVA, or even correlation, we always focusing on one dependent variable and one independent variable. So they are being used to explain the relationship between only two variables, right? So if you mark the independent variable as the x and you mark the dependent variable as the y, as you can see in the previous four hypothesis test, the very easy one we mentioned before, the chi-square t-test and ANOVA correlation, we only use one x to explain the y, or sometimes we say we use the one x to predict the y. We only use one independent variable to explain one dependent variables. Okay. However, in the regression, we still only have one dependent variable, which is a y, but we have multiple independent variables. Okay, we may have x1, x2, x3, x4, and to predict the y. So make an example like the y is whether a person is going to commit a crime or not. So this may be related to the person's age. This may be related to person's race, may be related to person's educational level, may be related to person's like a family income, or it could be one more, a lot of more like x5 is maybe the person's social status, x6 may be the person's current, economic status, x7 may be the personal like psychological traits. These are maybe these are this could be the impact or the impactor to this dependent variable like white person commit a crime, but they don't have to be. And even sometimes they seems to have the impact on this y, but whether the impact is significant or not is the thing we are going to study. Okay, so from here you can see like as I mentioned before that in criminal justice or criminology or even social sciences, most of the time when we're going to explain one variable's impact on another variable or the one independent variables impact on one dependent variables, we typically say that we're controlling other variables, right? In the previous analysis like this one-on-one situation, one x, one y, it's really hard to say that we control the other variables because you don't even include other variables into this analysis. You only have one x and one y, right? However, for the regression analysis, we do include other variables. So every time when we're going to talk about what's the impact of x1 on the y, since we include x2, 3, and 4 into our analysis, so we can safely say that we control the x2, x3, and x4 when we make a comparison just based on what's happening in the x1 and its impact on the y. So this is a thing that we previously we talked about, that controlling for other important variables. In order to do that, you have to include like as many independent variables as you can into the data analysis, but there will be some limit, and we will talk about those limits like in a couple of minutes. So some of the good thing that when we have the regression analysis is like we can make a guess about the cause and effect. Okay. Now previously when we have the chapter or the PowerPoints about the correlation, right? We say that correlation doesn't necessarily mean it's a causality. It doesn't mean two variables are highly correlated to each other, significantly correlated to each other, but it doesn't mean necessarily mean one causes another, because most important thing is because there might be other variables involved. So when we do in multivariant, or what we call the multiple independent variables, we include them here, then we can safely say that we include lots of the variables, and when we're going to interpret the one of the independent variables, that we can safely say we control the other independent variables. So this may help us to establish a cause and effect, but also the cause and effect needs like a proper time order and a theoretical connection, something like that. But that's not um, that's not really how why we need to control the third variable. Okay, and also it is a criterion for making solid causal interpretation, like I just mentioned about control the other factors from the other variables, and control the what's happening. Maybe there is a third or fourth variables. So in this slide, basically talking about um, that if we want to explain the x1's impact on the y, and we include x2, x3, x4, then we can safely say that if the x1's impact on the y is a significant, then it does really have some impact on the y. Okay, and also we say this one by controlling other variables. So the multiple regression equation in general, the equation will be looking like this. It's this one is look more like a linear regression um, formula, but as you can see, this is a linear formula, and some parts of that, for example, the y is a dependent variable. We always use the y to represent the dependent variable. The x is an independent variable. As you can see, we have x1, x2, 3 until xn. So these are the all independent variables that you include in the regression analysis. We also have the beta, which is a slope coefficient that measures the individual impact of the dependent variable on the independent impact of an independent variable on a dependent variable. So we have the coefficient for each of the x. You can see that. So each of the x are it is going to impact the y differently. Okay, some of the x may have a large slope coefficient, maybe they have a big impact, and some of them may have a smaller coefficient, maybe they have a less impact. But that's also based on like how you're gonna code the x and the y. We will mention this a little bit later. Okay, but the interpretation of the coefficient is that at this moment, unlike the chi-square ANOVA t-test or correlation, in these regression analysis, when you're going to interpret, for example, the x1's coefficient, that the beta one, then you have to put a sentence like while holding other independent variables constant or while holding other variables constant, because like I said, once you're using the multivariate regression analysis, then every time when you explain one variable, you're literally holding other variables in the equation constant, so you can make a good explanations. We also have the alpha, which is the intercept, the constant when all the x are equal to 0, what look like the y will be, and also we have the error term, that is other explanatory fact variables that is not included in the model. In criminology, criminal justice, or other social sciences, when we run in the regression, we do our best to include every independent variable that we think can impact the dependent variable. But the reality is that we couldn't include every of them because of the data set, because of the nature of the social phenomena. Which it's just we can't include everything else. So there will always be like an error term in all the regression analysis, is something we can't include in our data analysis. Those variables, we don't know what they are, or sometimes we know what they are, but we just couldn't include them into data analysis because the data doesn't have it, or we couldn't um, collect it at the beginning. Okay, um, so one of the important assumption in the multivariable model is that we assume the independent variables are independent of each other. Okay, in other words, is that we think those x1, x2, x3, xn, they are independent from each other. They are not highly correlated to each other. Okay, so a great regression analysis, or ideal regression analysis, when we're going to pick the independent variables, that we are going to pick the independent variables are very strong related to the dependent variable, and also weakly related or unrelated to each other. This is a very important. If you don't do that, then you will face the issue is that some of the independent variable will be correlated, and it will mess up the equation. It will mess up the data analysis process, and also it will make it difficult to identify which of the variables are influencing the dependent variable, because they all sort of measuring the similar things. Okay, so in practice, what happened here is that if it's happening, then we just pick one of the two variables and use it in our model. Okay, so some of the examples when I run some data analysis by myself is like when we're going to explore like the police department, the police organization. Sometimes we use um, the officers in one police department, and also we include like a budget. But as you know, like if the police department has a lot of police officers, that means it's a large police department, and large police department naturally having more money, right? Naturally having more funding, more money. So when you take a look at that, most often like the police officers population in the police department is highly correlated to the department's funding, or the money in the department. So the thing we're gonna do, or I would do, is to just delete one of the variables. Sometimes I use the population of the police officers in the departments. In other scenarios, I may use just the total fund or total budget in the police department to represent it. Okay, it will happen when you are not carefully selecting those independent variables. But again, ideal regression analysis, whether we're going to use linear regression, which will be talked about in this PowerPoints, or logistic regression, which will be talked about in another slides, another PowerPoints, then the ideal regression analysis always require you to select independent variables that are strongly related to the dependent variables, and only weakly or even unrelated to each other. It's very important. Okay. So for the regression analysis, this is the intro level of the stats. So what we're focusing on is the one for the dependent variable is a continuous variable. We use the OLS regression, the linear regression. When the dependent variable is a categorical variable with only two groups, we talking about a binary logistic regression, which will be discussed in another PowerPoints. When the dependent variable is categorical with three or more groups, there are different ways to do that. One of them is multinomial logistic regression, but we are not going to cover it in this intro level class. So the regression analysis, basically, it is a little bit harder to calculate by hand. So most likely we are going to use the software, and most likely we are going to focusing on the interpretation of those coefficients and rather than calculate those coefficients. So doing so, it will help people who are interested in reading criminal justice or criminology academic articles, or even other academic articles in social sciences. Okay, so if I focus in the regression analysis, the first one is the R square or adjust R square of the model. The second will be the F test of the model. The third, fourth, and the fifth will be related to the individual variables, the significance of the variables. Now, typically in the data analysis software, they use little stars to represent the significance level. One usually means a 0.05 level, alpha level. Two usually means 0.01 alpha level, and three usually means 0.001 alpha level. Okay, and also we discuss the direction of the coefficient of an independent variable, one independent variable, the value of the coefficient of that variable. Okay, so let's just go to the very simple linear regression, the OLS regression. You don't need to really know like how the OLS regression model runs, but it is the most common regression that we're gonna use when the dependent variable is a continuous variable. There will be some other assumptions that has to be met when we're going to use the OLS regression, but in this intro level class, we are not going to talk about them. Okay, so the most common we will be using is the linear regression, and as you can see, this is very similar to the previous formula when we talk about the basic regression. What does a regression look like? Okay, so the y, again here, the y is a dependent variable, the x is independent variable. We have multiple independent variables, right? The b is the slope coefficient for each of the independent variables, right? And we also have the alpha intercept and also the arrow term. We are not going to really focusing on them. So when we're focusing on this one, again, we're focusing on the previous we talked about is the R square F test, significance, direction, and the absolute value. Okay. Again, five focus. I'm just going to skip this thing. Okay. So first of all thing, let's talk about the R square. If you do remember when we talk about R square, we actually talk about the R square in correlation, right? Remember when we reject the null hypothesis in the correlation, we have the R and we calculate the R square in the correlation, and we put a sentence in the correlation talking about what kind of percentage that of the variance in dependent variable can be interpreted or can be explained by the independent variable, right? The R square's logic is the same in this linear regression. Okay, so the R square also gives you information about what's the percentage of the variance in dependent variable can be interpreted by independent variables. Here we have multiple variables, so it can be interpreted or it can be explained by multiple or by all the independent variables here, right? And also in the stats software, most likely you will see in linear regression, you will see a R-square and adjust R-square. There is a difference between the R-square and the adjust R-square. R-square assumes that every single variable explains the variation in the dependent variable, when the adjust R-square tells you the percentage of variation explain only the independent variable that actually impact the dependent variable. Okay, so typically what we do is that in practice, some people would pick, most people would pick to explain the R-square, when some other people would pick to explain the model with adjust R-square. But I think based on my readings, R-square is a more common way for people to use, because most of the analysis will not have or independent variables are to be the significant impact. So the adjust R square is always very small. So people tend to use the R square to interpret how much the variance in the data or in the analysis is explained by the predictor variables. So you put a sentence similar to what we did in the correlation. Okay, it is a proportion that can be converted to a percent, interpreted as a percent of the variance in the dependent variable that can be explained by all the independent variables. Okay, that's the R square. So we can just stick to use the R square. For example, if the R square is 0.66, then 66% of the variance in the dependent variable y can be explained by the independent variables x1, x2, x3, whatever you use in this formula or in this data analysis. Okay, so the logic of the R square is exactly the same as we interpret the R square in the correlation. Okay. The second is the F-test. This F-test also is sort of the ANOVA in the regression. It's not going to be the same as the ANOVA we see before, but the logic is the same. Okay, so the F-test also in the regression, the F-test has the same logic, is that the null hypothesis it will be all the coefficient is equal to zeros, or R square equal to 0. R square equal to 0, what does this mean? So 0% of variance in the dependent variable can be explained by independent variables, right? 0%. That basically means, well, this model has no independent variables, right? The alternative hypothesis is like the R square is not equal to 0, or here, as you can see, the R square is always like larger than 0. So if you put unequal or large, they are both correct. So that means like at least some of the variables is kind of a significant impact on the dependent variables. Okay, so in other words, I just give you an easy way to understand the F-test. In other words, the F-test of all significance indicate whether the linear regression model provides a better fit to the data than a model that contains no dependent variables. So what it is comparing is that it compares the model 1 that has all the independent variables. It compares a model 2 that has no independent variables, and the null hypothesis means those two models are the same. Okay, it has nothing different. The alternative hypothesis will be like the model 1 is significantly different from the model 2. Okay, so in practice, in general, if you run the regression analysis and by using the correct or proper independent variables and select the proper dependent variables, you should have an F-test that is less than 0.05. So the p-value of the F-test is supposed to be less than 0.05. So if it's less than 0.05, we can reject the null hypothesis, right? So we say that the model has independent variables is like better than the model has no independent variables. That's just most of the situation. If you run the regression correctly or properly, this is something you will get. Okay. The coefficient has two things. One is the direction. Of course, the positive coefficient indicates that the value of the independent variable increases, the dependent variable also increase. The negative coefficient means that when the independent variable increases, the dependent variable decreases. So you can see the direction here is just similar to the direction to the thing we talk about in the correlation, right? The positive correlation means x increases, y increases. The negative correlation means x increases when y decreases. So it's the same logic. And also the values in the linear regression or even OLS regression suggest that how much the dependent variable changes given one unit shift in the independent variable when holding other variables constant. While holding other variables constant is a very important sentence every time when you're going to interpret the coefficient. Okay, and I will give you some examples later. So just this is just brief introduction. So the example here, okay, so you can see um, the dependent variable will be public attitude toward the police officer 1 to 10. Okay, so 1 means you are not really satisfied with the cops. 10 means that you are super satisfied with the cops. The independent variable here, we have a bunch of them, right? We have the age of the respondent, gender of the respondent, educational level of the respondent, the fear of crime from the respondent, and what do they think about the quality of life from the respondent. So what if the coefficient of age is 0.05? What does this mean? Okay, typically we have three ways to say that. The first one is a mathematical way, or it's a really from a math perspective. Okay, so as one unit increases in age, about 0.05 units increase in public attitude toward police officers. Okay, so if the respondents are getting one age older, then their attitude toward the police officer will get 0.05 unit increase. That also means like if the people are who are 10 years older, then that would be 0.5, right? So if they are 20, so it would be 1. So let's assume there are two people. One is age 20, another person is age 40. So based on these results, it looks like the age 40th people, let's say if the age 40th people has a attitude toward the police officer as a 7, then the age 20 people should have the attitude toward the police officer as 6. Okay, a 20 age gap leads to 1 unit change. A 10 age gap leads to 0.05 change. Okay, it's a way that you can explain what's happening from a mathematical way, but in reality or in practice, the most common thing you will see is at the bottom. So the most important thing we want to know is the direction in social sciences. Okay, so if the age is positive, then compared to young people, older people tend to be more in favor of the cops, right? It's a positive. Or you can say age is positively related to the public attitude toward the police officer, or age is significantly positively related to the public attitude toward the police officers. When people are getting old, they are more likely to be in favor of the police officers. That is the most common thing you will see in practice. Okay, but if you write this sentence, this is not wrong. Okay, it's just a in most of the time when we wrote academic papers, we don't really put that sentence into it. So some of the examples you can see, those are the from actual paper. Okay, so what we have here, the dependent variable is police public contact duration measured by the minutes. So every time when the police contact the public, we measure the time that how long they gonna stay on site. Okay, sometimes they stay 5 minutes to write you a traffic ticket, or sometimes they spend like 15 minutes to write you a traffic ticket. So we want to see like what are the factors that may impact this duration. So we have the independent variable measures as the right side. Okay, so we have measure if the citizen is a female. yes or no. If the citizen is a juvenile, if a citizen is a non-white, so if it's yes, then they are non-white people. If it's no, that means they are white people. Intoxicated, maybe under the drug, under the alcohol, lower class, that basically means the social class. Whether this is a situation, is a assault situation in this police public contact situation, or whether there is arrest involved. As you know, like look like if we have arrest situation, the police is supposed to spend more time, right? They arrest people and they write those reports, so they should spend more time. Whether there is an injury happen in this incident, and also whether there is a citizen disrespect to the cops, they talk dirty to the cops or something like that, or whether there are bystanders that people are watching these things, or whether they are like whether the officer is a female officer or whether the officer is a non-white white officer. COP, that's a community-oriented policing. Okay, if you know a little bit about the policing, that community policing requires the police officer to have more communication with the public. So we assume this may be increase more time when they are in the police public contact situation. And also the length is like the length of the service, like how many years this cop has been a cop. Okay, so what do you see on the left side is the variable and the regression we run. This is a beta and this is a t-value. It doesn't matter. The only thing we're focusing on is little star. Okay, if there are little stars, that means this variable is a significant variable. If it's not, then it means this variable is not a significant variable. Let's interpret some of the variables here. For example, we're focusing on like the significant data, a significant independent variable. The one lower class. The lower class, the coefficient is negative. It's a significant. So what does this mean? That means if a person, if this situation happens to a citizen that has a lower social class, then the police tend to spend less time in this situation. Okay, how much time they spend less? It's like about average 8 minutes or average like 9 minutes less when controlling other variables. Okay, so another one is assault situation. So this is also a had 3 stars. This is a significant variable. So the assault situation basically means like if the police public contact situation has involved in an assault, whatever the assault is, then the police officers are going to spend more time in this contact. Okay, how much time they spend more? It looked like they spend like a 16 or 17 minutes more when they're dealing with this assault situation. Now, similarly, you can see if there is an arrest involved in this situation, then the officers are going to spend like about 9 minutes, 10 minutes more in this situation. Okay, when we're talking about those significant variables, we always say we're holding other variables constant. Okay, so again, once we can see in the officer characteristics, there is a community policing involved. So when the officer has been assigned with community-oriented policing job, or they have been trained by the community-oriented policing, then they tend to spend more time in the police public contact. And what time they spend more? They probably spend 10 minutes more when controlling other variables. Okay, regarding other things, you can see like say female citizens. Okay, if a citizen is a female, the police officer tend to spend less time, right? Did you see that? This is a negative. If the citizen is a female, the officer tend to spend less time in this situation. However, this less time is not a significant less time. So we don't need to explain those variables are not significant in the results. Okay, so in theory or statistically speaking, the citizen's gender has nothing to do with the police public contact. although we can see they may reduce the time about 4 minutes based on the coefficient, this is not a statistically significant impact. So statistically speaking, the gender of the citizen has nothing or has no significant impact on the police-public contact duration. The similar applies to whether a citizen is a juvenile, whether the citizen is a white or non-white, whether the citizen is under the drugs, under the alcohol. They all are not all of them are not the significant predictors of the police public contact. So we don't really have to interpret them in our final writing, when you're writing the reports, when you're writing the results, something like that. Okay. So another example is the public satisfaction with the police. 1 means the low satisfaction, 10 means the high satisfaction. Okay, similar, we have the age measured by years. We have gender measured by male and female. Education measured by, this is like a college education, so yes or no, whether they own the house, whether they are satisfied with the prior citizen police experience, whether they are not satisfied with prior citizen police experience, or even they don't have any previous contact with the cops. The fear of the crime, 4 is the highest. Whether the respondent was a victim of the crime, yes or no, and the neighborhood conditions. So, and they measure the neighborhood conditions from 11 to 33. It's a added scale, something like that. 33 means there are lots of bad things happening in the neighborhood. The environment or conditions in the neighborhood is bad. Okay, so again, here we are looking at the variables that has a significant impact. So with those little stars here, right? So you would see is that first of all, gender. So the gender is going to be a negative correlate, a negative coefficient. So that means if the gender from female to male, 0 to 1, okay, the gender increase from 0 to 1, then the public satisfaction with the police actually decrease. So what does that mean is compared to female citizens, the male citizens tend to have a less public satisfaction with the cop. Okay, the males are less likely to be satisfied with the cop when holding other variables constant. Similarly, college education. So from 0 to 1, but it's a decrease in the dependent variable. So what we interpret is college education. So when people, compared to the people who have no college education, the college education people seems tend to be less satisfied with the police. Okay, the people who had received a college education may tend to have a low satisfaction with the police. They may think the police could do better based on their education. Okay. So we also have the prior citizen police experience, and the dissatisfaction is a huge impact here. So what does that mean? It means like if a respondent had a previous citizen police experience, whether it's a traffic stop or other things, and he is not or she is not was not satisfied with the previous experience, then this will impact their perspective about the place at this moment. Okay, so like I got pulled over by a cop a year ago, and I was not really happy about the thing. I'm not happy. I'm not satisfied about why this cop pulled me over. And then after a year, when you come to interview me, like how do you think the cop's doing? I would remember this dissatisfaction situation and say, no, I don't like the cop. Okay, that's a meaning of the dissatisfaction in the prior citizen police experience. And we also have like a victimization. So again, the victim increase like from 0 to 1, so the coefficient is a negative, so the satisfaction with the cop decrease. So this tells us like if the if a respondent was a victim of the crime, the respondent is less likely to be satisfied with the cop, which doesn't make sense, right? If I'm the victim, and maybe the cop didn't even solve the case for me, then of course, I'm not happy about them, right? I'm not really being satisfied with them, right? Also, the neighborhood conditions, as you can see, from 11 increased to 33, and the coefficient is also a negative number. So this basically tells us if the neighborhood gets worse, the people who lived in the neighborhood may getting less satisfaction with the cop. Right. Sometimes you see the neighborhood, you may have the drug issues in the neighborhood, you may have the crime issues in the neighborhood or burglary issues in the neighborhood, and the people are blaming the cops. They are not doing anything. So um, this result does make sense, right? So sometimes we use like the SPSS to analyze the data. We use the Stata or like those professional software to do the data analysis. But sometimes we use the cheap one, the Excel, to analyze the data. So again, if you use the Excel to analyze the data, you will also see the coefficient here. I don't care what is the dependent variable, but you can see the independent variable like GPA, age, drinks per month, marijuana use per month, something like it. Look like a what GPA, some sort of like drinks marijuana, like college students. Okay, whatever. So you will see the coefficient here. And whether the dependent variable is, I don't really care. But as you can see, the GPA is a positive, age is a positive, drinks per month is a positive, and marijuana use is a positive. But this doesn't mean they all have the positive impact on the dependent variables, right? What we do is we're gonna see this little p-value, and again we say that the p-value is set up, usually set up at 0.05, right? If it's less than 0.05, then it is a significant predictor. We reject the null hypothesis. We accept the alternative hypothesis, so it is a significant predictor. If it's large than 0.05, then we fail to reject the null hypothesis. We have to accept that this variable is not a significant variable, or it's not a significant predictor in predicting the dependent variables. So you can see whatever here GPA, the coefficient of GPA, age, drinks marijuana here is, the p-value of drink is 0.05, which is bigger than 0.05. Which the zero point 0.5, okay, which is bigger than the 0.05. The age is almost 0.80, which is bigger than 0.05. The drinks per month is 0.10, which is bigger than 0.45. The marijuana use is 0.21, which is bigger than 0.05. So based on this p-value, none of these variables, GPA, age, drinks per month, or marijuana per month, is a significant predictor of the dependent variables. Okay, I don't really care what is the dependent variable is, but based on the p-value here, none of the p-value is less than 0.05. That means none of the predictors or none of the independent variables here can be a good predictor or can be a good factors in predicting or explaining the dependent variables. Okay, that's it.